Remember how both Barb and I struggled with math in school? We're not alone. So many students feel the same way. But here's what amazes me, both as a mathematician and an educator. When students are given the right support, their growth can be incredible. I've come to believe that to truly understand a mathematical concept, I need to break it down into its most intuitive core, something a child could grasp. Not because math is always simple, but because clarity is essential for learning. Those brain scientists in France found something that fits with this. Even expert mathematicians use some of the same basic brain networks that kids use when learning math. Through practice and learning, these networks get better and better at handling complex ideas. I've seen overwhelming evidence for this belief in my work with thousands of students. Let me share a remarkable story that illustrates this. When I started jump math 25 years ago, one of my first students was in a remedial class and hadn't learned how to multiply numbers, even though she was in grade 6. She was testing at a grade 1 level, and the school thought her IQ was 70, and she was extremely anxious.
Incidentally, this student's situation illustrates what happens when neither learning system is properly developed. Her declarative system was overwhelmed by basic calculations, and she hadn't built up the automatic pathways that would have made those calculations automatic.
In our first lesson, I taught Lisa to multiply by skip counting on her fingers. For example, to multiply 3 times 2, count by 2s until you've raised 3 fingers. The number you say when you've raised the 3rd finger, 6, is 3 times 2. When Lisa saw that she could multiply, she became less anxious and started to learn at a much faster rate. Her mother told me that she had a nightmare about not being allowed to go back to tutoring because I was the first person who told her she could do math. In my second lesson, I started to show Lisa, using diagrams and models, why various operations with fractions work. But I had to break down all my explanations into the smallest possible steps. For example, put your finger on the smaller denominator. Skip count by that number. Did you say the other denominator as you were skip counting? How many fingers did you have up when you said the number? This methodical, step-by-step approach gave Lisa's declarative system the time to process each piece of information, while repetition helped her build automatic fluency. Over time, she began to work on more complex topics with less support. As her automatic system developed automatic responses to basic operations, her declarative system became free to tackle more challenging concepts. 3 years later, after only 120 hours of tutoring, she'd caught up 9 grades and entered academic grade 9. Then she skipped a year and finished grade 10 math in the same year. Here's an example of a question she was able to solve independently on her tests.
To make furniture polish, you can combine lemon oil and mineral oil in the ratio 3:200. How much lemon oil do you need to make 10.15 liters of polish?
On the test, she had to use different methods to solve a variety of ratio problems. So she hadn't just memorized an equation. She had to understand each problem and take the right approach. Working with thousands of students, I've learned that I should never assume a student is incapable of doing math, no matter how challenged they appear to be. What looks like inability is often just an underdeveloped automatic system combined with an overwhelmed declarative system. I've also seen the power of deliberate practice and of the principles of instruction that we discussed in the first lesson.
Incidentally, let's add a little more information about the basal ganglia's automatic system. It's often dismissed as involving lesser rote-type learning. But this system is essential not just for recall, but for recognizing patterns and developing intuition. Think about how you learned your native language. It wasn't just about memorizing a jumble of individual words. It also involved a deep, intuitive understanding of the language's structure, like grammar, sentence flow, and common expressions. Over time, this basal ganglia type understanding became so automatic that you can now speak and comprehend your native language effortlessly, even picking up on subtle nuances without even thinking about it. Much of this was done by your basal ganglia system. This same system underpins how we develop an intuitive feel for math. It doesn't just store facts like 7 times 8 is 56. It helps you see relationships and patterns, like how 7 times 8 relates to 7 times 7. You just add another group of 7. This system allows you to feel patterns in math, building an internal sense of structure that makes problem solving faster, more accurate, and more natural. Coming up, we'll see how these ideas apply to neurodiverse learners. But meanwhile, let's give you some practical insights related to teaching math in the classroom.